بسم الله الرحمن الرحيم.
Dear students, today we will go through lecture 7 of organic based industries. This lecture is actually extension of lecture number 6. In this lecture we will go through polystyrene production and application part 2. In this lecture the key concepts will include different forms of polystyrene, then the manufacturing process for expanded polystyrene. Then we will compare extruded polystyrene and expanded polystyrene, a brief about structure particularly focusing on tacticity of polystyrene, and in the end we will go through degradation, specifically biodegradation and environmental hazards attached with polystyrene chemistry. Polystyrene is a synthetic aromatic hydrocarbon polymer made from the monomer known as styrene. Polystyrene can be either in the form of solid or in the form of foam. General purpose polystyrene is clear, hard, rather brittle. It is inexpensive resin per unit weight. Polystyrene exists in 5 different forms: high impact polystyrene, commonly known as HIPS; expanded polystyrene, commonly known as EPS; packing peanuts; extruded polystyrene, commonly known as XPS; and oriented polystyrene, commonly known as OPS. High impact polystyrene is a versatile, economical and impact resistant plastic that is easy to machine and fabricate. High impact polystyrene is often specified for low strength structural applications when impact resistance, machinability and low cost are required. Expanded polystyrene, it is a white foam plastic material produced from solid beads of polystyrene. It is primarily used for packing insulation. It is closed cell rigid foam material produced from styrene, which forms the cellular structure, and pentene, which is used as blowing agent. It means expanded polystyrene is a mixture of the cellular material as well as the blowing agent, where cellular material is compulsorily is styrene. Both styrene and pentene are hydrocarbon compounds obtained from petroleum and natural gas byproducts. Packing peanuts. Packing peanuts are polystyrene fragments that are incorporated into packing of fragile items like glass items, with the goal to prevent product from moving inside the box during distribution. Some of these peanuts are made from biodegradable materials. Extruded polystyrene. Extruded polystyrene foam is a rigid insulation that has also formed with polystyrene polymer but manufactured using an extrusion process. That's why it is called extruded polystyrene. This type of insulation can significantly reduce buildings' energy use and help to control indoor temperature. The last class is oriented polystyrene. Oriented polystyrene is produced by stretching extruded polystyrene film. improving visibility through the material by reducing haziness and increasing stiffness. This is often used in packing where the manufacturer would like the consumer to see the enclosed products. Some benefits of oriented polystyrenes are that it is less expensive to produce than other clear plastics such as polypropylene, polyethylene terephthalate, and high impact polystyrenes. It is less hazy than high impact polystyrenes or polypropylene. The main disadvantage of oriented polystyrene is that it is brittle and will crack or tear very easily. Polystyrene exists in two distinct forms. These are solid polystyrene and foamed polystyrene. Foamed polystyrene is particularly expanded polystyrene, packing peanuts, and extruded polystyrene. Generally, foamed polystyrene materials are processed in three different ways. First method utilizes gravity-fed or air-fed polystyrene into closed molds, then heated to expand up to 50 times their original volume. In second method, polystyrene is pre-expanded by heating and then molding in a separate processing operation. Whereas the third method includes polystyrene extruded into sheets. How expanded polystyrene is manufactured? The conversion of expandable polystyrene to expanded polystyrene is carried out in three different stages. These are pre-expansion, maturation or stabilization, and last one is molding. Polystyrene is produced from styrene, which is crude oil refinery product. Expanded polystyrene manufacturing involves impregnation of polystyrene beads with foaming agent pentane. Polystyrene granulate is pre-foamed at temperatures above 90 degrees centigrade. It means the polystyrene solid granular is converted into foamed granulate above 90 degrees centigrade. This temperature causes the foaming agent to evaporate and hence inflating the thermoplastic base material to 20 to 50 times its original size. After this, the beads are stored for 6 to 12 hours, allowing them to reach equilibrium. Then beads are conveyed to the mold to produce forms suited as per application. During final stage, the stabilized beads are molded in either large blocks or designed in custom shapes. The material can be modified by the addition of additives such as flame retardants to further enhance fire behavior of expanded polystyrene. Over here we are going to discuss two different industrial processes for the preparation of expanded polystyrene. These methods are post-impregnation suspension process and in situ suspension process. In this slide, we are going to discuss post-impregnation suspension process. This process is essentially a two-part process using two process lines in series. In the first process line, raw styrene monomer is polymerized and a finished polystyrene bead is produced. Don't confuse, this is solid transparent polystyrene bead. The second process line takes the finished bead from the first line, impregnates the bead with a blowing agent and produce a finished foamed polystyrene. Figure in the slide is a schematic representation of this process. In the first line, styrene monomer, water, initiator and suspending agents from the basic charge to the suspension reactor, which is unit number 1. The styrene to water ratio varies with the type of polystyrene required. A typical ratio is about 1/4 to 1/2 monomer to water volume, means water is double than monomer. Initiators are commonly used because the reaction temperature is usually too low for adequate thermal initiation of polymerization. Suspending agents are usually protective colloids or insoluble inorganic salts. Protective colloids are added to increase the viscosity of the continuous water phase, and insoluble inorganic salts such as magnesium carbonate are added to prevent coalescence, merging union of the drop upon collision. In the reactor, the styrene droplets are suspended in water phase by using mechanical agitation and suspending agents. Droplet size may vary from about zero point 0.1 to 1 millimeter. The reactor is heated to start polymerization, which takes place within the droplets. An inert gas, nitrogen, is frequently used as blanketing agent in order to maintain a positive pressure during the cycle to prevent air leaks. Once polymerization starts, temperature control is typically maintained through a water-cooled jacket around the reactor and is facilitated by the added heat capacity of the water in the reactor. The size of the product beads depend on both the strength of agitation and the nature of monomer and suspending agents. Between 20 and 70% conversion, agitation becomes extremely critical. If agitation weakens or stops between these limits, polymer particles may agglomerize, followed by a runaway reaction. Polymerization typically occurs within several hours, the actual time varying largely with the temperature and with the amount and type of initiators used. Residual styrene concentration at the end of reaction are as low as 0.1%. Once the reaction has been completed, essentially 100% conversion, the polystyrene water slurry is normally pumped from reactor to a hold tank, which is unit number 2, which has an agitator to maintain dispersion of the polymer particles. Hold tank have at least three functions. First function is the polymer water slurry is cooled below 50 to 60 degrees centigrade, which is heat distortion temperature of polymer. Second function is chemicals are added to promote solubilization of suspending agents, and third function is that tank serves as a storage tank until the slurry can be centrifuged. From the hold tanks, the polymer water slurry is fed into said centrifuge, which is unit number 3, where water and solids are separated. The solids are then washed with water, and the wash water is separated from the solids and is discarded. The polymer product beads, which may retain between 1 and 5% water, are sent to dryer, which is unit number 4. From the dryer, they may be sent to a classifier, unit number 5, to separate the beads according to size, and then to storage bins or tanks, which is unit number 6. Product beads do not always meet criteria for further processing into expanded beads, and off-spec beads may be processed and sold as crystal polystyrene. In the second line, the product bead from the storage bins of the first line. Water, blowing agent from unit number 7, and any desired additive are added to an impregnation reactor, unit number 8. The beads are impregnated with the blowing agent through utilization of temperature and pressure. Upon completion of impregnation process, the bead water slurry is transferred to a hold tank, which is unit number 9, where acid may be added and part of water is drained as wastewater. From the hold tanks, the slurry is washed and dewatered in centrifuge, unit number 10, and then dried in low temperature dryers, unit number 11. In some instances, additives from unit number 12 may be applied to expanded polystyrene beads to improve process characteristics. From the dryer, the expanded polystyrene beads may undergo sizing, if not already done, before being transferred to storage silos, unit number 13, or directly to packaging, unit number 14, for shipment to the customer. Second industrial process for the manufacturing of expanded polystyrene is in situ suspension process, which is shown schematically in figure presented on slide. The major difference between this process and the post-impregnation suspension process is that polymerization and impregnation take place at the same time in a single reactor. The reaction mixture from the mix tank unit 1, composed of styrene monomer, water, polymerization catalyst and additives, are charged to a reactor, which is unit number 2, to which a blowing agent is added. The styrene monomer is polymerized at elevated temperature and pressure in the presence of blowing agent, so that 5 to 7% of blowing agent is entrapped in polymerized bead. After polymerization and impregnation have taken place, the expanded polystyrene bead water slurry follows essentially same steps as in post impregnation suspension process. These steps are repeated in figure.
packing foam, but its real name is expanded polystyrene packaging, those feather-light white foam inserts that come with many boxed items. They not only secure the merchandise within the box, they also act as a shock absorber during transport. Polystyrene plastic comes in tiny pellets about 1 millimeter big. The first step is to expand them inside a steam chamber. The 200 degrees Celsius heat causes the pentane gas in the pellets to escape, allowing air to enter the pellets and inflate them up to 40 times their original size. Here are the polystyrene pellets before and after expansion. The factory then bags the pellets in huge sacks. To make expanded polystyrene products, they start by dumping sacks of expanded pellets into what's called the block mold machine. The more pellets they put per cubic meter, the denser the product will be. They steam fuse the pellets together, molding them into a block that's roughly 5 meters long by 1 meter wide by 3/4 meter high. This molding process takes from 5 to 20 minutes, depending on the density. A scale built into the conveyor belt weighs the block to make sure it meets specifications. Depending on its density, a block this size can weigh anywhere from 45 to 200 kilograms. Now the block is ready to be cut into whatever product the client has ordered. Expanded polystyrene is best known as a packaging material, but it also has many other uses. Here, they're slicing a block into insulation panels. Builders use expanded polystyrene insulation for basements, roofs, foundations, and inside and outside walls. Regardless of the product, they cut polystyrene blocks using a copper and nickel wire that's electrically heated. It melts the polystyrene on contact, enabling fine precision cuts almost to the millimeter. To make expanded polystyrene packaging, they custom cut the specific shapes required. These squares they're gluing together have been ordered up by a furniture manufacturer. They're designed to fit onto the bottom of chair legs to protect them from damage during shipping. This machine handles more detailed and complex jobs. Its cutting wire is guided by computer software, so it can cut virtually any design. Expanded polystyrene is a low-cost alternative for making commercial signs that can be hung indoors or out. A sign made of high-density expanded polystyrene and coated with a quality exterior paint has an outdoor lifespan of a few years. This moldable product has endless creative and commercial uses.
Attention Culver City business owners. Beginning in November of 2017, Culver City says no to polystyrene, also known as number 6 plastic. Polystyrene comes in two forms, the commonly known expanded soft foam and the less commonly known hard compact plastic. The polystyrene ban will prohibit the sale of both forms of polystyrene. Polystyrene foam food containers include items such as plates, bowls, clamshells, and the hot cup. Single-use polystyrene hard plastic includes items such as straws, utensils, clamshells, sauce containers, water cups, and hot cup lids. While two items may look similar, if you check the recycle symbol to see which number plastic it is, you may find that the plastic you're using may be polystyrene, and not a friendly or recyclable plastic like PEAT1. If your item doesn't have the plastic number on it, contact the manufacturer or the vendor. There are a multitude of alternatives available for bulk purchasing. Many of these alternatives can be found by the same companies providing polystyrene items for purchase. Here are just some of the websites that offer polystyrene alternatives. Many food establishments in Culver City have already replaced polystyrene. Some have switched to completely reusable products, which in time has proven to save money. In addition to the ban, food vendors will now provide single-use takeout cutlery only upon request from the consumer. The polystyrene ban will apply to all restaurants, grocery store delis, hotels and motels with restaurants, convenience stores, farmers markets, and retailers. Penalties for not complying with the polystyrene ban are a $100 fine for the first offense, $200 for the second offense, and a $500 fine thereafter. Culver City is here to help our businesses as we make this ban a reality. For more information and resources on polystyrene alternatives, please visit culvercity.org/polystyrene ban or contact Environmental Programs and Operations at 310-253-6423.
To most of the people, extruded polystyrene looks similar to expanded one. But it is not the case. Both are different in processing techniques as well as in morphology. Expanded polystyrene uses beads already treated with foaming agents. It is just fusing them together by heat and pressure, whereas extruded polystyrene utilizes solid polystyrene bead and foaming agent as starting materials. Heat and pressure melt these ingredients and make a homogeneous matrix which is extruded into sheets. Expanded polystyrene is molded into blocks which are then cut into desired shapes. Expanded polystyrene has many empty spaces or voids between foamed beads. It is because the blowing agent leaves the beads due to molding process. On the other side, extruded polystyrene has no voids or empty spaces as blowing agent is embedded in the material.
The expanded polystyrene foam industry has stated their product EPS performs the same, if not better, than extruded polystyrene rigid foam insulation or XPS. The emphasis is on performance, specific to R value and moisture. But you only have to look at the science to see the truth. Science doesn't lie. Let's start with the differences in manufacturing. With the XPS continuous extrusion process, a homogeneous closed cell matrix is produced through the entire cross-section of the foam. This matrix of closed cells resists water penetration, and that's important because water penetration can reduce R value if absorbed into the insulation. With the EPS cell structure, the bead molding process leaves voids between beads where water can enter. Although the individual beads of EPS are closed cell, the voids between the beads can absorb water, which reduces the already lower in-service R value of EPS. ASTM C578 tests are important to measure and quantify the properties of each material. What you see here is a demonstration of how each, Owens Corning's XPS and EPS handle water commonly found in a 1.5 pound material. In real-world applications, insulation gets wet, but it still must perform. When EPS absorbs water, its R value actually decreases, even when tested at lower temperatures. In fact, EPS exposed to water has a lower R value at 40 degrees Fahrenheit than it does at 75 degrees Fahrenheit. This water absorption also subjects EPS to damage during the freeze-thaw cycle, which can have a negative effect on product integrity. XPS continues to have a higher R value at lower mean temperatures even when exposed to water. In higher density EPS products, the fusion of individual beads is better than lower density EPS products, but the problem still exists. Foamular XPS features 0.3% water absorption by volume across all ASTM types, meaning potential to absorb is very unlikely. Now EPS features 2 to 4% water absorption by volume across all ASTM types, meaning EPS potential to absorb is 10 times greater than Foamular XPS.
Resisting water is critical for high-performance insulation because water is a good conductor of energy. So if water gets into the board, it lowers the thermal effectiveness of the board. Water allows energy to short-circuit or bypass its way through the board structure and really reduces the effectiveness of the insulating power. XPS, because it doesn't absorb water, doesn't have those short circuits in it. XPS is a closed cell structure and maintains its insulating power in the presence of water because water can't get into it and create those short circuits.
Owens Corning's Foamular XPS rigid foam insulation is well suited for multiple commercial and residential applications. Here's why. It has the industry's only lifetime limited warranty for the life of the building or home. Only XPS has achieved GreenGuard Gold certification with strict certification for occupants with sensitivities. Only XPS has third-party certified recycled content by scientific certification systems with a minimum 20% recycled content. XPS is available in multiple thicknesses with straight tongue and groove and scored-squared edging. And it's reusable, and remnants from manufacturing are recycled back into new XPS foam insulation. From wall systems to whole building solutions, work with an industry leader who continues to take the industry forward. Put our experts to work for you.
In polystyrene, tacticity describes the extent to which phenyl group is uniformly aligned in polymer chain. Tacticity has a strong effect on the properties of plastic. Standard polystyrene is atactic. The diastereomer, where all the phenyl groups are on the same side, is called isotactic polystyrene, is not produced commercially. Atactic polystyrene, the only commercially important form of polystyrene, in which phenyl groups are randomly distributed on both sides of the polymer chain. This random positioning prevents the chain from aligning with sufficient regularity to achieve any crystallinity. The plastic has a glass transition temperature of 90 degrees centigrade, and polymerization is initiated with free radicals. Syndiotactic polystyrene can be produced by using Ziegler-Natta polymerization, with phenyl groups positioned on alternate sides of hydrocarbon backbone. This form is highly crystalline with a melting temperature of 270 degrees centigrade. Polystyrene is a durable thermoplastic that is generally believed to be non-biodegradable. Actually, biodegradation of polystyrene does occur, but at a very slow rate in natural environments, and therefore polystyrene persists for long periods of time as solid waste. Polystyrene is relatively chemically inert. While it is waterproof and resistant to breakdown by many acids and bases, it is easily attacked by many organic solvents. It dissolves quickly when exposed to acetone, chlorinated solvents, and aromatic hydrocarbon solvents. Because of its resilience and inertness, polystyrene combusts incompletely as indicated by sooty flame. The process of depolymerizing polystyrene into its monomer is called pyrolysis. This involves using high heat and pressure to break down chemical bonds between each styrene compound. Pyrolysis usually goes up to 430 degrees centigrade. The high energy cost of doing this has made commercial recycling of polystyrene back into styrene monomer difficult. Polystyrene is generally considered to be non-biodegradable. However, certain organisms like superworms and mealworms are able to degrade it, although very slowly. The droppings of these worms were found to be safe for use as soil for crops. In fact, a large number of microorganisms can bring about styrene biodegradation. There are several ways of styrene catabolism. However, a predominant pathway involves the oxidation of styrene to phenyl acetate, which is then converted via TCA cycle. This pathway is shown in figure. In order to reduce environmental pollution caused by polystyrene, some solutions have been applied, such as reducing the use of polystyrene products and using modified polystyrene materials that can be biodegraded in environment. There are several environmental hazards associated with polystyrene products. These hazards include global warming, non-biodegradability, hazardous if improperly burned, and carcinogenic. Global warming. Extruded polystyrene is usually made with hydrofluorocarbons, which have global warming potential of approximately 1000 to 1300 times that of carbon dioxide. Non-biodegradable. Discarded polystyrene does not biodegrade for hundreds of years and resistant to photolysis. Hazardous if improperly burnt. When burnt below 900 degrees centigrade, up to 90 dangerous compounds can be released. Some of these are alkyl benzenes and carbon monoxide. Carcinogenic. The styrene monomer is cancer causing agent.